Buenos días. Ah, estoy muy feliz hoy porque mi español está mejorando. Am, Estaba escuchando los podcasts en español y yo comprendí mucho. No comprendí todos, pero comprendí mucho y por lo tanto estoy muy feliz. Y yo quiero intentar hablar contigo en español. Después de mi lección hoy, vamos a hablar en español. Um, uh, el podcast se llama Conversaciones en Español y las otras lenguas. Y ahí ellos hablan sobre las bebidas y los alimentos y las cosas que nosotros encontramos en la vida diaria. Aprendo mucho. Okay, I think I'm going to start. So I have a pretty easy lesson for you today. So what we're going to talk about today is what if you have a circuit that looks like this. So we have a battery, and then we have a wire, and then we have no resistor. Okay? We have no resistor. So maybe the battery is a 10-volt battery, something like that. So the question is, how much current is going to flow in this circuit? And the answer, well, if we were to just apply Ohm's law blindly, well, current is equal to volts divided by resistance. So the voltage is 10 volts. And the resistance, well, there is no resistor. So the resistance value is 0. So that, of course, if you have 10 divided by 0. Now in physics speak, you divide by 0, you get infinity. Okay? So that means that the current that flows would be infinity amps. Okay? So there are two problems with this calculation. I almost wrote problema. There are two problems with this calculation. And these are the first problem is the subject of today's lesson, and the second problem is the subject of Thursday's lesson. So the first issue is that even if you have zero resistance, so it is possible to have zero resistance with things called superconductors. Okay. Batteries cannot output infinity amps. Okay. So batteries are basically what's happening in a battery is you have a chemical reaction, and as the battery is making charge flow through it, that chemical reaction proceeds forward, and as you learned in your chemistry class, there's a rate of reaction. Okay, so there's a certain maximum rate of reaction, and so that the speed at which charge can go from one side of the battery to the other is limited by that rate of reaction. Okay, so that's what we're going to talk about today. But let me just mention the second problem, or the second issue, is that non-superconducting wires have resistance. Okay, it's a small amount of resistance, but they have resistance. Okay, so basically, and actually, even superconducting wires have resistance. You might have heard of AC versus DC, alternating current versus direct current. Superconductors only have no resistance at DC. If they're AC, then if you have an AC current, then even superconducting wires have a resistance. Okay. So today's lesson is about real batteries. So basically what we're going to do is we will learn about a more realistic model for batteries. Okay, and so it's very simple. So if you have a real battery, so what is the opposite of a real battery? Well, the opposite of a real battery is an ideal battery. So an ideal battery can output infinity amps. Okay, so an ideal battery can output infinity amps, but if you have a real battery, the model of a real battery is different. Okay, so a real battery actually behaves like it has a resistor inside it. Okay, so that's how a real battery behaves. So basically, even and so a real battery behaves like an ideal battery So this would be an ideal battery in series with a resistor. So this resistor has the effect of limiting the current, even if you have no external resistance. Okay. So a real battery behaves like an ideal battery in series with a resistor. Now, typically, this resistor is called little r, okay, as opposed to big R for external resistors. Okay, so big R is going to be external resistors. All right, so those are the ones that are in the outside circuit. And then little r is called the internal resistance. Okay. It's called the internal resistance of the battery. And usually it's around 1 ohm. So if you have actual resistors, you go to the resistor store and you buy resistors, then those resistors are typically hundreds of ohms to thousands of ohms to even millions of ohms. So to have a 1 ohm resistor that's a small resistance. So the internal resistance is typically small, and that's why it's denoted by little r. And then so this battery that is inside the battery, if you will, is an ideal battery. So this one could output infinity amps, but it never will because it's always in series with this resistor. Okay? And so that is typically denoted by curly E. And curly E is the voltage of the ideal battery inside the real battery. All right. So this is typically what is printed on the side of your battery. Okay. So they print out the big E value. Now that is called the EMF of the battery. So basically on the side of a battery, the EMF is printed. And that is called, so EMF stands for electromotive force. So remember how I said voltage is like a force that causes current to move. So electromotive force, that's pretty much exactly what it says, right? Electron moving force. Okay? So, these, now I want to point out that this is just a model for a real battery. If you take a AA battery and you saw it in half, you're not going to see, it's not like those nesting dolls, right, where you're going to find another battery and a resistor, and then you can saw that open, you find another battery and another resistor. Okay, there is no actual resistor inside the battery. This is a model representing how the battery behaves. Okay, so there is not actually a resistor inside the battery. It just behaves as if there was one. Okay, so don't go sign up your batteries looking for resistors. You'll get acid on yourself anyways. So when you have a so if I said that if you have a circuit that looks like this, Okay. You have a circuit that looks like this, where this is a real battery, and this is the external resistance, then what you actually have what you actually are going to have is that real battery should be replaced with an internal resistor and then an ideal battery with an EMF E. So, and here's the external resistor. So notice how the internal resistor and the external resistance are in series. Okay, so the current that is going to flow is going to be the voltage divided by the total resistance, where now we are including the external resistance. Okay, so the current that flows is going to be the EMF divided by the external plus the internal. Okay, so this is going to be the amount of current that will flow. So, yeah. And please keep in mind that these two resistors are not in parallel. Okay, even though they're both pointing in the same direction, they're not in parallel because there's remember I said in the last lesson that things are in parallel if you can do a loop around the circuit with only those two things. So this circuit only has one loop, and no matter what, the battery is in that loop. So these two are in series. Now this actually gives us a nice rule, okay? It makes it obvious. So most of the time, you can neglect the internal resistance. You know, why did I teach you about ideal batteries before real batteries? It's because most of the time, the difference between the two doesn't matter. All right, and we can see why it won't matter. So see how the external resistance is added to the internal resistance. Most of the time, the external resistance is much bigger than the internal resistance. Okay? And so what that means is that when we add these two together, it's still approximately the external resistance and the current isn't affected. Okay? So we can neglect the internal resistance, which is little r, when the external resistance is much bigger than the internal resistance. Okay? Otherwise, we must include it for an accurate calculation. Okay? So most of the time, I don't even think about the internal resistance. But if I had a circuit where my external resistor was like 1 ohm or something, you know, that would be approximately the same size as the internal resistance. So then I would be thinking, I have to worry about the internal resistance. Okay. So there's another effect. Okay. There is another effect of internal resistance. Okay. Basically, because of the so I'll just write it out. There will be a voltage drop across the internal resistor. All right, because the internal resistor is going to have current flowing through it. And so as a result, according to Ohm's law, it's going to have a voltage drop across it. And this means that the external resistance will get less current, or less voltage, excuse me. Okay, so you might have a battery with an EMF of 1.5 volts, but even though the battery has an EMF of 1.5 volts, the circuit is not actually going to receive 1.5 volts because there's a voltage drop across the internal resistance. So that is often called drooping or sagging. All right. So basically what happens is the harder you push the battery, the more severe the droop will get. Okay. So let's see how that works. If I have a real battery, so here's a real battery. We have an external resistor. Okay. We have the internal resistance and we have the EMF. Okay, so the voltage that the external circuit gets, that the external resistance gets, is going to be the EMF minus the voltage drop across the internal resistor. Okay, so this internal resistor eats up some of the voltage that the EMF provides. By the way, this circuit is essentially a voltage divider, right? Because it's two resistors in series and a battery. Okay, so this is expressing the voltage divider equation. The internal resistor obeys Ohm's law. So the external circuit is going to get a voltage that's equal to the EMF minus the current that flows times the value of the internal resistance. Okay, so this is going to be the voltage that the external circuit gets. So this is Ohm's law applied to Ohm's law applied to little r. Okay. That in this second term here. So the voltage that the external circuit gets is called the terminal voltage. All right. because the battery has two terminals. It has a positive terminal and a negative terminal, so terminal voltage. All right, so that's pretty much the content. Oh, by the way, the internal resistor, because it has current flowing through it, it's going to dissipate power. And we know that resistors take energy and convert it into heat. So if you've ever taken a battery and noticed that it's getting warm, we could calculate the rate of heat production as the power being dissipated by the internal resistance. Okay, so that's kind of interesting. So let's do an example, and then we'll be done. Okay, so what if this is my circuit? This is 2 ohms. This is 5 ohms. And this is, actually, I'm going to make this 6 ohms, 5 ohms, and 4 ohms. Okay. And this is a real battery with EMF equal to, let's say, 12 volts, and an internal resistance equal to 1 ohm. Okay? So even though I've drawn it as an ideal battery, I'm saying it is a real battery. Okay? So what I'm going to do is I'm going to redraw this circuit. Okay? So I'm going to redraw it, taking into account the fact that this is a real battery. I'm going to draw the internal resistance up here. So this is 1 ohm. This is 12 volts. Okay. And then that gets fed into these 3 resistors in parallel. So that's 6 ohms, 5 ohms, and 4 ohms. Okay, so the first thing I want to do is I want to figure out how much current is going to flow out of the battery. So the current that flows out of the battery is going to be the EMF divided by the total resistance. So including the internal resistance. Now, hopefully you can see by this point that this circuit is 3 resistors in parallel, and then we combine those, and then that is in series with the 1 ohm. Okay, so I'm just going to write that all in one step. So my total resistance is going to be the 1 ohm plus the 6, 5, and 4 in parallel. And remember, this is the formula for 1 over R parallel, so I have to do the -1 of that. Okay? So let me work that out in my calculator. And so that I get that the amount of current is 4.58 amps. Okay? So this is the amount of current that flows out of a real battery. Okay? Now, what if I neglected the internal resistance in this case? What if I assumed that this was simply an ideal battery with 12 volts? Well, in this case, my current would be E over R tote, but now I'm neglecting the internal resistance. So now I have 12 over, and so I don't have this plus 1. I just have 1 over 6 plus 1 over 5 plus 1 over 4 to the negative 1. Okay. So if we neglected the internal resistance of the battery, we would have only gotten, or we would have gotten 7.4 amps. So you can see that in this case, there is a significant difference between what the battery is actually going to give you and what you might calculate if you neglected the internal resistance of the battery. Okay, so this would be a situation where we would not want to neglect the internal resistance because things are going to be very different from what we expect. 3 amps difference. So another thing I could ask is, what is the terminal voltage? Okay. So the terminal voltage, remember, is the EMF minus the voltage drop across the internal resistance. Okay. So the EMF is 12. Okay. And then the current, we're going to use the current that actually flows, not the ideal current. So 4.58 times the internal resistance value, which is 1 ohm. And so that is going to give us 7.42 volts. All right. So you are expecting to get 12 volts, but you hook it up to your circuit and you only get 7.42. Again, that's a big difference. So in certain situations, the internal resistance is incredibly important. And I'll ask one more, which is, what is the rate of heat generation from the battery? As I said, the internal resistance generates the heat of the battery, okay? So really what I'm asking is, what is the power dissipated by the internal resistance? Okay? And so that is going to be, there are multiple equations for power, but I'm going to use the I squared R version. Okay? So again, this resistance is only the internal resistor. I'm going to use the actual current that flows, 4.58 squared times the internal resistance, which is 1. And so we get about 21 watts would be, so 21 joules of heat per second are produced by the battery. Now this is kind of interesting. That would cause the battery to heat up, and when the battery heats up, that will in turn change the EMF and change the internal resistance. So all of these parameters of the battery are temperature dependent. Okay, so that's kind of cool. They're also dependent on time. You could think about a battery, running out of charge. You could think about that as the internal resistance becomes infinite. So as time goes on, that internal resistance grows until it becomes infinite, and then no current is going to flow out the battery. The battery is dead. So that's pretty interesting, I think. So this is a useful model. Again, don't go sign into batteries looking for the internal resistance. It's a representation of how the chemical reactions inside the battery make the battery behave. Okay? So that is my lesson for today. And I will see you in the Zoom room, and hablaremos en español.